Hi, everyone, and welcome to our Brass on Robotics talk series. I am Ani Shia, and I'm your faculty host. I am very happy to welcome Dr. Guillaume Sartoretti from the National University of Singapore. So Guillaume is an assistant professor in mechanical engineering and has been doing very interesting work in distributed and decentralized coordination of multi-agent systems. In fact, he's trying to bridge this gap between stochastic modeling, conventional control, and AI. So I was first introduced to Guillaume as when he was a PhD student by one of his committee members. And at the time, Guillaume was working on stochastic modeling of large teams of robot, which is an area that we in my group also do. And he just reminded me that the first time he came to the US to spend 6 weeks, right, working with us back when I was at Drexel, he came to Wu and Chen because I was giving the GRASP talk that week. So it's great to have him back at Penn. And for me to be able to welcome him, to Penn, and to welcome him back to Philadelphia and to be giving our talk today. So we are joined by PhD students Ben Schaefer and Tom Zhang. So Ben is in mechanical engineering and applied mechanics, and then Tom is in computer and information science. Those are the departments. Just a quick reminder, our panelists will assist in directing your questions to our speaker during the Q&A panel at the end of the talk. If you're joining us via Zoom, please submit your questions using the Q&A button at the bottom of your screen, and our panelists will make sure, right, that they get answered during the panel session. So without further ado, Guillaume, take it away.
Thank you very much. Thanks, Annie, and thank you very much, everybody, for being here. It's a big honor. It's kind of a dream come true. So I wanted to talk about some of my recent labs and personal work initially for the postdoc in control of large-scale robotic multi-agent systems, right? So to start with, let's ask the question, how do you control a large group of agents, right? And as many of you may know, we have this spectrum of approaches going all the way from centralized control. We have one agent in charge of the entire team, usually centralizing information, and then distributing even sometimes command inputs or control directly to all the agents. So the big advantage there is performance guarantees. You're able to tractably approach those systems. You can obtain optimality guarantees with respect to some metric, usually time to complete the task or energy constraints, etc. You also can have what we call completeness in some cases, the ability for the system to guarantee that if a solution can be found, it will be found, sometimes by exhaustive search, right? But of course, you're also paying some prices. The scalability is not amazing. Combinatorial explosion of the search space, and you're vulnerable to single agent failure. If an agent breaks down, then it's a difficult, usually replanning is involved, but you have to detect the failures. And in the worst case, if the central agent falls, then the whole system is down, right? And of course, you're also relying on usually global and constant communication to report back to the central agent. And that can also be a burden in real life application. Despite this is what we're seeing the most in the world, right? Amazon's Kiva, formerly Kiva, now Pegasus system, a lot of existing warehouses also. A lot of this, because the scale of the system is not so large and because of the control nature of the system, they still remain fully centralized, right? But the goal is really to push to the other side of the spectrum, going for decentralized control. So here the idea is every agent is in charge of its own destiny, understanding its own situation, understanding maybe its partial observation of the system, and make individual decisions. As a result, you're very scalable. More agents means more computation. So, and of course, you're very robust to agent failures. If you see someone not doing this job, you can easily step in and help. So you're robust to additions and attrition of agents. You usually don't rely on global communication. You can do local comms only, but you're losing guarantees, right? Those systems are very much not tractable as a result. So you don't really get any guarantees, and you're very often suboptimal with different degrees of suboptimality. And then what I care about a lot, which is going to be a big portion of the talk today, is cooperation, the explicit reasoning about joint actions. is a lot more difficult to obtain in decentralized system, right? It's very difficult to ask the question, how should I act based on what you will do? Because it becomes the symmetric, oh, but I think you do this, but you think, I think that you think, et cetera, et cetera. So reaching consensus and getting those joint decision-making going is very difficult, right? And that's going to be a bit of what we talk about today, right? Inspiration here comes often from nature. This is one of my favorite examples. It's an ant raft. So fire ants, when the colony is underwater, they congregate into those bowls, and the bowls is buoyant because all the ants being in it, right? But most of the ants, a good portion of the ants are underwater and some are over water, and they all trust in the system that they'll be allowed to move in and out of water for everybody to survive until the raft goes to a safe place and they can rebuild. And that's fully decentralized, fully out of local interactions, stigmatic and like chemical interaction between the ants. In robotics, there's been some work. This is from Radhika Nakmal's group at Harvard. It was the first 1,000 robot team, right? And this is fully rule-based system where they're learning to create those patterns. And agents do not know where they'll be in the pattern. First, they don't know where the starfish is going to be created. They don't know what part they'll have to play in it. But through local rules and densities, they start figuring out this consensus on how should I fit in so we can make this thing happen, right? And so the big lesson here is, well, first, it's very impressive, right? But the big lesson here that I want you to think about is this relies heavily on the intuition, the experience of the designer, right? This is not yet robots being clever as much as someone being really clever at telling them what to do, right? And so while this is a very good step towards decentralized control, I think we can all agree that the goal would be to get to the level that humans and most social animals can have of, being able to figure out your own solution instead of just, being told a cool rule, right? And that's going to be where machine learning comes in the mix. Before we do this, I just wanted to go through this. So this is going to be kind of the outline of the talk, right? It is not my work. This is from Amanda Prorock at Cambridge, a few people like MIT, and then a few people from Ben that you can recognize, right? And they've been proposing this terminology for the different multi-agent problems that exist, right? The 3 C's: coordination, cooperation, and collaboration. I used to use those words a bit differently in the past, but I think it's a really cool terminology, so I kind of want to promote it, right? And so on one hand, you have coordination, where the alignment, the entanglement between agents is usually weaker. So you can think of agents doing their own thing and maybe trying to avoid being in the way of each other, like avoiding collision, right? So they don't need to be tightly coordinated. And as a result, you can expect usually sublinear gain. Like as the team grows, you're not going to get like the overall task done twice as fast with twice as many agents, but you'll still get a bit more from having more agents, right? In the middle, you're getting into cooperation, right? So here, the alignment between the agent's objective is very strong, and you can expect at least linear and sometimes even like threshold-enabled gains. So this is an example where agents are trying to find a target from a base station and need to have local communication and connectivity. So in this case, you see that if you have too few agents, you're not solving the task. And then suddenly when the team size is enough, then immediately you can get like essentially 100% success. And you have this big threshold in the middle, right? For me, what is really interesting here is that this is also where I would start thinking about and mentioning the fact that joint action selection is important. Like this fact that, again, agents might need to take actions because they interlock with each other, because they allow you to enable those coordinated maneuvers that are very important in some cases, right? And I'll show you many examples later. And then on the end, we have collaboration, which is essentially reserved to heterogeneous robot systems, where having robots with different capabilities allows you to have those coordinated maneuvers that result in more than the sum of their parts. So we're really in like 1 + 1 is greater than 2 territory here, right? And so we can expect that this complementarity of capabilities, the synergy that they can identify and leverage will result in superlinear gains, right? And so today, I'm going to tell you a bit about what I've done that was initially in the coordination realm, right? That was mostly during my postdoc at CMU. And then what my team and I have been starting to do in cooperation and collaboration domain, right? So that's going to be essentially the outline of the talk. So to start with, I like starting with a task. And for me, we will get back to this one a few times, right? But one of the central tasks I've been focusing on is multi-agent path planning. So it's very interesting, for automation, but also like, airplane taxiing, autonomous vehicles. There's a lot of application, very central problem. So very simple. I have a bunch of agents. They each have a goal that I've pre-assigned some way, right? And the goals are assigned to each agent. There's no swapping or anything, right? And I just want them to get to their goal as fast as possible. In a domain, I can assume they already know everything. So it's a static map of which they know the obstacle map, right? And I want to avoid obstacles with collisions with obstacle, but also collision with each other. Those are the really tricky ones, right? And so this is an example with 200 agents finding a path in this scenario. I like this example because if you go very naive, if you go centralized planning on this one, the calculation was that there is not enough RAM on the planet to look one step ahead. Because you're looking, every agent has 9 movements, 8, and then stay in place. 9 to the 200 is an astronomical number, right? And so this is not something you can look ahead naively. And so initially what people did when they approached this problem was go fully centralized, extend A star to like a centralized A star and search in the joint configuration space of the agents. Clearly that breaks down very fast, right? So then people actually went way the other way with the pendulum, and we went to decoupled approaches, right? The idea there is you have each agent plan their own path, and then you're trying to make those paths work. So either adapting velocity, maybe if there's a collision, we'll slow down an agent or speed up another one. But sometimes in like frontal collisions, that doesn't work. So then you can allow agents to bypass and go around from that path, right? So those are very nice. They scale well, but they're strongly suboptimal in practice, and they result in paths that are not really feasible or like promising for application, right? And so recently, there's been this push for what's called dynamically coupled approaches. Those approaches, they do individual planning, and they only locally deal with joint search when there's a collision, right? So the idea is everyone does their own path, and when we discover there's a collision, then we either backtrack and search through the joint space of those agents, or we add constraints and things like this. So it works really well, and in practice, so this is planning optimally on the left and suboptimally on the right. So the blue one, A star, you see it breaks down very fast. Like this is something that even 10 agents optimal you can't do. If you're going for bounded suboptimal and with some tricks, you can get it a little bit more, but really you need to go for something a bit more clever. But despite this, those dynamically coupled approaches are at best linear. They start breaking down at a few hundred agents. So this is a bit of an older plot, but the new ones, because the problem is combinatorially exponential, if you give me like Moore's law, like a few years to like double, quadruple, sextuple the computation, I'm still only going to be able to maybe give you 1, 2 more agents you can plan for. So when I started looking at this problem, I was like, this is a very interesting kind of saturated domain. And I don't know if pushing on this front is really going to give us like the next frontier. Like, what if I want to do 1,000 agents? And so my idea here was, what if we leverage the fact that this is a very symmetric problem and try to go back to decentralized approaches, like fully decoupled, but we're trying to remove all those drawbacks from like having defined the best rules we can do, and then seeing that, of course, they're limited by our intuition. And so the idea there is, I know this problem is very symmetric. I know that every agent is trying to understand its local context, right? And avoid collisions, but also try to go to their goal, right? There's those kind of 2 objectives. It is such a symmetric problem that maybe we can learn one policy that all agents can enact. That doesn't mean that they will do the same action at the same time. It means that in the same situation, they would react the same way. So it also gives us a bit of harmony in the system. And so the big advantage there is if I can learn this common policy, if I can assume that this common policy exists because the problem is symmetric, then I can also learn it faster. And so the idea there was to extend some work on distributed learning for single agent system to the multi-agent domain, right? And so now I can learn the symmetry faster. So I can learn this policy faster the more agents I have, because I can leverage their all experience and have more training data to do it. And then the main thing is at the end, I have a policy that is essentially single agent now. It has the collaboration baked into it. I can copy it onto as many agents as parameter sharing for the ones that know it, right? And so that was really the core of what was like an emerging like framework, like paradigm at the time, the CTD, centralized training. So at training time, I can centralize information, in this case, the policy, right? And then at the end, I'll still have an execution that's purely decentralized. The way we did it, I'm not going to go into too much detail, but it was exactly like this. So this was the HVC, like a distributed single agent algorithm, and then we pushed it to a multi-agent scenario, right? So every agent looks at its own state, decides its own action. That creates this vector of action that is enacted, in this case, in a random order, right? And then each agent will receive a reward from it, and then we do it again. And at the end of the episode, each agent reflects on what it has seen, calculates its own gradients, its own lessons, and they're all pushed to a central repository that contains the most complete policy we have so far. We do this until convergence, and at the end, this central policy is the one we will deploy and copy on all agents. Yes. No, I'll show you exactly the state, but no. For now, they're all anonymous. So it's a bit more akin to kind of like a mean field kind of thing, where you know yourself and you can see others. You know that there are dynamic, there's obstacles and there are other agents, but you don't know which one is which. And so that's why it scales really nicely, right? A big thing like the number, like the ID or something like this. Yes. So we didn't really want this. We wanted like this kind of anonymity. And yeah, so what you're saying is right. Like if you actually introduce IDs, like the number of the other agents, you might have essentially priority-based roles that are learned. And we didn't want this. Yeah. But you can also do it. It's just something we didn't want to do. That's a good point. Yeah. So the way we actually did it is the first question was, a lot of people looked at multi-agent path planning from a learning point of view. And the big problem was the scalability of the world, right? If I have a world that can change in size, I can't make the entire world my input to my neural net. Otherwise, if the world changes, even becomes smaller, I have to retrain. That's not good. So we went with this idea of a small field of view around each agent, right? And in this field of view, we broke it down into channels, kind of an image, right? And we gave binary information. So presence of obstacles, yes or no. Presence of other agents, which are all the same. It's just there is an agent, there is no agent. If there are agents around me, I'll tell them where their goal is. And if their goals are outside the field of view, I'll just project them to the boundary. So I can see agents are going in those general directions. And then for myself, if my goal is within line of sight, then I'll tell you exactly where it is. So I can do like precise planning. If the goal is not close to me, which is often the case, then I'll give you a global vector pointing to this goal. So I'll give you like a normalized vector and the distance to it. The idea is with this, I should be able to navigate in this general direction and then deal with local collision avoidance threats. The way we do it is we rely on two things. First thing is half of the episode randomly, we do them very traditional reinforcement learning. We have a collaborative reward structure, right? Oh, sorry, I did the imitation learning. Okay, but so half of the episode we do imitation learning and we learn from a centralized planner. So we learn to copy a planner that has full knowledge of the system, can enact those coordinated behaviors, and we're trying to learn this type of scalable joint action selection that are difficult to find. And the other half of the episode, we're learning them through reinforcement learning, so just through trial and error, right? In this case, we're relying on some cooperative reward structure where we're teaching the agents to go to their goal as fast as possible, avoid collision, and then mainly when they're on their goal. For example, the red one here is on this goal. If it doesn't move from the goal, the blue one cannot reach its goal. And so in this case, the red one will learn that it is blocking. That's an additional output from the system that they learn to figure out, and it gets penalized. And so in this case, agents are learning to go to their goal as fast as possible, stay on it, the one-shot problem, except if they're blocking somebody else, in which case they should move. This is what it looks like. So in this case, this is 5 agents trying to exchange with 5 agents at the bottom. And in the middle of the bottleneck, we have another agent. So again, pure selfishness, no solution, because the middle one would not have any incentive to move. But with this blocking prediction and rewards penalty, the pink agent is learning to essentially take a walk, move out of the way, and let the other ones do it. So for now, you can all observe that it is working. It is not very pretty, right? I mean, they're learning to get out of the way, but it's not like a principal way to it. There's not like, I'm going to try to get out and be energy efficient. It's just like, I'll get out and then I'll come back later on when it's like fixed, but I have no idea when. It scales really nicely. So this is a case with 80 agents. So train with 8 agents, tested on 80. And I've highlighted a few places where you can see those behaviors. Again, not very pretty, but very efficient, right? They allow you to go through and not have those selfish blockage happen. And then again, train with 8 agents. This is what happens when you scale very well. And so you scale to 1,000 agents. So that was the first time that we were able to get to this next order of magnitude of agents. And here agents are making individual decisions to their goal based on only this local 10 by 10 field of view around their position. And this is, yeah, go for it.
At this point, there's no kind of global coordination.
No, exactly. Surely decentralized.
Do you know that leads to kind of weird pathology where there's no symmetry based?
Yes.
Kind of all agents that are the same path or something like that.
Oh.
You can imagine an allocation problem, let's say that there are 2 different allocations, and then all these agents because they're symmetric and maybe deterministic, I'm assuming, they all kind of take path A because they make the same exact.
Because it's closer. So we didn't have this. Yeah, so we didn't have this too much because we're in training. We tried to be careful that they learn. Oh, Oh, yes, sorry, yes, yeah. So the question was like, do we have pathological cases that happen because because the policy is homogeneous, maybe they all prefer the same and they create like a bottleneck, like they prefer the same bottleneck and then they create a traffic jam. So we didn't have this too much. They learn in scenarios that are very dense. So they make sure that they learn by seeing many agents around themselves. And I think they, naturally discover that if something is blocked, then I'll go the other way. And I think in practice, it's kind of okay. The full symmetry ones, they are not good at. Like there is one bottleneck, both people want to go through. They'll either both go or both wait. And that's the problem. So this is going to be like the improvements I discuss later. But the kind of distribution thing, we kind of got it for free through the training. But that is something you can like also like bias the training to kind of, represent more. Oh, yes.
Like one solution, traffic.
Yes. It's coming. No, good. Yeah, the question was about like, what about adding more like traffic, like external information, like a semaphore or traffic lights to give more coordination? Yeah, so that's what we did in the next one. Yeah, I'll get to this in a second. No, that's good. So we did it on robots, of course, and the big advantage here is most approaches until then were one-shot, like offline planners. So the idea is I give you the problem, you do as much planning as you need, maybe 5 minutes, and then at the end you give me a path and I just execute it. The problem there is if the robots don't do what you want, you have to replan, and again, it's 5 minutes. Here it's a purely reactive planner. So that means that we are just choosing what to do every time step. And so if something wasn't enacted, if actuation was a problem or whatever, we'll just redo it. And if we add an agent, like here the 5th one was added, the system just naturally adapts to it. It's a purely reactive system. There is memory, but this is not enough to really break it. And so we get those very promising, very advantageous benefits of a reactive planner, which for robotics, very advantageous. Yeah. That's been nice. We also applied this to other problems. So we did like, extension for like foraging, like multi-agent foraging. We're doing some work on multi-agent traffic scenario control also, right? Another problem that I like was the collective robotic construction. This is the Thermos problem, also from Radhika Nathal's group, right? So agents are charged with constructing a 3D structure. And they can go and pick up those block elements. They can place them down, and they can go up or down exactly one way. So they need to figure out like where to place them, but also create the right scaffolding to be able to reach higher places. And sometimes scaffolding need to be built and then removed at the end because they're not necessary for the final structure. So initially, they had like a rule-based decentralized system, but only if scaffolding was part of the structure. And our big advantage was that by allowing agents to learn to do it, this is they're learning to build this castle, and they're figuring out those scaffolding that are necessary by themselves. So they're learning to add the necessary blocks they need to get those higher places reachable, and then remove them at the end and clean up the sticks, right? So it is not very efficient. We've done like better since then, right? But the idea there is, again, like, a decentralized system, learning essentially a rule that maybe humans could have handcrafted, but it's very difficult to find. So really, like, learning as a way to improve on decentralized, like, kind of rule-based system. We've also done this for completely different, oh, sorry, go ahead.
The previous slide was very cool. I was wondering how.
Yes, so we don't, okay, so the question is, how do you measure suboptimality here, right? Like you mean like precisely, right? Yeah. So we didn't fully do it precisely because at the time there was no optimal multi-agent planner for it. Now there has been work from USC, Satish Kumar's group, Sven's student, that have done like a pure, a guaranteed optimal planner even for multiple agents. So we could calculate it. In our case, we had more of an estimate of how suboptimal it is, right? But it's more like visually. The scene is changing? Oh, yeah. So we were looking at the optimality of the overall plan. So we're saying like, based on where you start and what I want you to build, what is the smallest number of actions you need to actually make it happen? And then we're looking at how many we take, and we get an idea of, how more do we end up doing, right? So it's not a dynamic process, what I'm saying. You can really do it as a one-shot from start to finish. You should be doing it in 200 actions, but I'm doing it in 500, so I'm, 2.5 times longer than I need to, right? But I was not really centered on the suboptimality for this one. For multi-agent path planning, it's a lot easier because we have a lot of planners for this. This is more of a newish problem, and so this one we didn't have like the full, so we didn't focus on it. The next thing we did was going for a very different type of multi-agent system. And that's kind of what I like a lot, is going with a different type of robots. In this case, we're taking an articulated legged robot, and we're calling the different joints agents. And we're saying, let's have you work together on stabilizing the robot. So the goal here is to keep the body of this hexapod level and at a specific height from the ground. And we're allowing each leg to be an agent in charge of updating the joint angle of one of them to kind of get this leveling, right? And so the way we did it is we, again, like distributed training, because we have multiple agents and we're allowing each of them to make its own decision, but learn a homogeneous policy. We can learn 6 times faster, right? And because of it, we're able to learn a smaller policy with more data, so like really best of both worlds, and we get to do something that can be trained on robots in a pretty reasonable amount of time, like something like 45 minutes. If we do the centralized baseline, the blue one here, you see that even with like 3x the number of episodes, we see a trend up. We're not even close to converging, right? So the idea here is that we're getting something that's much faster to train because we have more data, but also we're training something that is much smaller, but easier to train, right? So we're really getting the big advantage. So you're seeing the training happen and you're seeing it like slowly get to a pretty okay level. The goal here was to learn feedback on an underlying locomotion controller. So the agent is doing a bit like silly moves, but that's okay because at the end, when we finish training, we can actually deploy it with the underlying controller and we get something like this where, oh, it's a bit slow. But yeah, we're getting something where the robot is able to like move with the underlying controller and use those feedback just for stabilization. And we get something that is very usable. The other big advantage was we're getting scalability like before, right? And so we're able to deploy the same policy on a version of the robot with only 4 legs and get something that naturally scales despite never having seen this specific scenario, right? We gave the joint angles. We also gave the... Yes, oh, no, only of that leg. So like 3 joint angles of the leg, 3 torque feedback of that leg, because we have a series elastic robot, so we can give the torque feedback, and then we gave a kinematic, like processed information about the shoulder, like height, essentially. That was the main one, because this is the one that says, are you too high or too low, right? Exactly, yes. And that was a way of essentially distributing global information at the local level. Yeah.
Kind of like opposite.
Yes, exactly. That was the idea, like going with something a bit like decentralized control, yeah. So that was really well. So now that was like the end of the coordination part, right? So now we've seen systems that are very homogeneous, but we're trying to get agents to coordinate without explicit, interaction. So we're able to answer the question, how do we work together towards a goal, but not really how do we complete this goal together, right? And so we looked a little bit more into multi-agent reinforcement learning, and you see the pictures appear on the right? Those are the different classes of multi-agent learning systems. And this is essentially what we call, so far what we've done is what we call independent learning. So every agent is learning their own policy, and with centralization, maybe like parameter sharing, but there is nothing more in terms of like tight cooperation. So since then, we've been looking at different ways. One of them was looking into convention learning, which is very close to the semaphore idea, right? Like adding signals maybe from the outside or adding rules that the agent should follow to bring harmony to the system. So I'll show you an example of this. We've also looked at one that is very exciting, communication learning, where agents are allowed to create their own language. So they're learning to encode their knowledge, so state, but also memory and other information they have into messages, and then share those messages with other agents. And now they're using their state as well as messages to make information. That should lead you to have more observability, of course, but also to potentially talk about joint actions and even like consensus. If you can actually make this system like stabilize, you can really get this type of dialogue that you need to reach a consensus and enact a joint plan, right? And then the last one that we've done most recently is closer to the like centralized critic, centralization idea for cooperation learning, context-aware decision-making. So we're allowing agents now to rely on a lot more information about the entire system. We're augmenting their knowledge and allowing them to build those context embedding they can then use to make local decision-making informed by global information. And that's really, in this global information is the cooperation aspect of the system, right? In this case, we also are doing a lot of asynchronous decision-making, which also helps with cooperation because someone acts and then you act afterwards, which makes it easier to make decisions of condition on the others. Right. The last bit that is common in multi-agent RL that we haven't done, this is the great part here. This is value decomposition. So here we're explicitly answering the question of who did what for the success of the team. And so this is approach like QNX, VDN. If you know about this, this is something that has been done a lot, but is not something that my lab has been doing. It's a more, you're learning heterogeneous policies, so it's a bit different. So let's go into it. So we extended this primal idea, multi-agent path planning, to the lifelong problem. So we extended it to two problems. The first one is this one shot. When an agent gets to their goal, they disappear from the system. So it's more of a, trains getting to a train station or a car getting to a parking, right? When you're there, you're not a collision for the other one. So it's a slightly easier version of the problem. The one that we cared about the most was this continuous one. So every time you get to a goal, you're going to get another goal assigned to you. So more of the really automated warehouse problem, right? And there the idea was, let's figure out conventions. So this is us like more figuring out the right conventions. Like there was semaphore, there were other methods like this, and then find a way of baking those conventions directly into the agent's policies to create this harmony at the whole system that looks like those coordinated maneuvers that you get from joint planning, right? So we did a lot of comparisons with existing planners at the time. We do a lot better. We can reach up to like 2,000 agents. We can actually do more, but it starts being very slow in just like testing because we still test centralized, sadly. But we're getting to a point where we're at least on par with much more improved search-based planners. But the big advantage is we're trading off this optimality versus computing time. Like other approaches, they still need minutes to get you plans. And we have a reactive approach that can do it much faster, even though we're not as optimal. We've done a few tests on those like benchmarks in the community, so warehouses and mazes, but we also were involved in the Europe's Flatland Challenge. That was what was driving this one-shot version. So there's a challenge on train scheduling. And so this is where we ended up #1 for the first round and then 4th overall. They changed in the program halfway through. So that was very good. Since then, we've been focusing a lot on communication learning as kind of like the next frontier to get this like really explicit joint planning. I don't want to like create good convention and then make them enact this. I want them to like figure out those things, right? And so one thing that we've been working on is on multi-hop communication. So in this case, we have a team of N agents, and we create N links, so directional LSTM networks between them, and we connect those agents together, right? And so what happens is that every time step, we have agents encode those LSTMs with their own information so far, and then pass this along to the other agents, right? And so we order the agents so that all of them are at the end of at least exactly one of the chains. And in a way, what happens here is that we get multi-hop communication every time step, where agents are encoding sequentially information on kind of like a node, like a notebook, right? And then passing it along. And at least one of the messages that each agent receives has been encoded sequentially by everybody else in the team. And that allows us to essentially get this sequential encoding, but at the end get a context that has been like encoded by everybody else. So get a message from everybody else, right? But of still a finite dimension. In terms of the overall structure, it looks like this. We have multiple agents, right? And they all directly connect to the different LSTMs that create this communication channel. The big advantage is by connecting agents this way, the channel is differentiable. That means that agents are learning how to do this encoding based on feedback from the recipient of the messages. So they're really saying like, how should I do better with my communication next time based on the rewards you got from my previous message? So it's really just, it's a more direct way of learning that's a lot more stable, a lot more potent, because they're really working together on like figuring out this good language, right? One big challenge of those approaches is that there's no memory. So we added a memory module also, so agents don't forget what they've seen at previous time step, because otherwise all of those are reset every time step, the LSTMs on the communication channel, right? And at the end, we concatenate. We've also done something with like transformers, so we can like scalably combine them, and that works even better, right? In terms of performance, so we've done a lot of testing on the StarCraft multi-agent challenge. That's like a big, open benchmark for cooperation, like where agents have to learn to fight with each other. Like they have a team of agents, homogeneous, and they're fighting another team in sort of skirmish. You'll see a few videos in a second, right? And there's a few easy problems, medium, and hard. We're comparing our variants with communication learning state-of-the-art approaches, and then those value decomposition I told you before. Those are state-of-the-art for StarCraft, right? They really learn heterogeneous policy that perfectly interlock with each other. We're doing pretty okay, as everybody does, on the easy problem. On the medium problem, you already see that we're the only ones of the communication learning methods that are able to kind of keep toe-to-toe with those value decomposition methods. Very likely because of this like global information that they can propagate in the team, right? And then when we start going for the very difficult problems, then we're kind of sometimes even outperforming something like QMix, which is very impressive. This is what it looks like. So in this case, I'm going to show you two videos. We're controlling the bottom agents in one and the left agent in the other one, right? And the goal is just, I have some time to give you. You need to essentially kill the other guys and not be killed. That's all, right? You can't just run away. That doesn't work, right? And it's very interesting because you see specific behaviors happen. Here you're seeing what's called kiting. So this agent is essentially capturing the attention of the enemy while staying like exactly at the right distance to not die in the process. And then easily the other guy can just shoot the enemy from afar. Very simple, but it's a 2v1, so it's a bit easier. Let's look at a 3v3. In the 3v3, they're still learning a somewhat similar scenario. The bottom one is going to be kiting two agents. So trying to run away, capturing the attention of two of them, while the other ones can win an easy 2v1. And then once this is done, they regroup, and then they'll have an easy 3v2 to finish, right? And this is purely learned strategies that they figure out through communication for those problems. Extending this idea and going back to multi-agent path planning, we've done an extension to what I showed you before. So like this is like the primal, just decentralized network that we've seen earlier, individual channels, global information from the vector, right? And we've added the idea of outputting a message for each agent and then receiving messages from other agents and then fusing them together with a pretty scalable transformer architecture, right? The big advantage here is that you're using attention to figure out of the messages around you, which ones actually matter. So you're going around what's called the chatter problem, where agents might get overwhelmed because they receive too many somewhat conflicting information, right? And you're able to really start getting agents to perform like nearly as well as a centralized planner because they can do a joint action selection. So we compared with state-of-the-art communication-based learning methods. The big advantage here was that because the communication was a lot more scalable, we're the first one that were able to go beyond a few hundred agents with pretty successful results, at least in medium density and low density scenarios. And now we're starting to see stuff like this, right? We're able to start agents getting out of the way in a lot more principled manner, not just run around and without understanding why I need to not be there. But really being able to have like those clear coordinated behaviors that we wanted to see. And you get to see those even at the global level, right? So I've highlighted a few in this like 32 agents, medium size of the world scenario, right? And so that's pretty promising, right? Again, scalability is the big problem with communication because you can't just scale to thousands of agents when you start sharing thousands of messages. This is very challenging. Going for the second, the last part of this middle portion of the talk, this is going into context-based learning. So the first thing that we did in this scenario, so no communication, but I'm allowing agents to now reason about a lot more of the knowledge, a lot more of the state of the world to still enact those very advanced cooperative maneuvers, right? In this case, we're focusing on multi-agent TSP. So I have a bunch of cities, I have a bunch of agents, they all start at the same location. They need to visit all cities so that every city is visited by one agent. So it's a distribution and path planning problem. There's been a lot of work on learning-based methods for the single agent TSP. And our idea was, can we push this to the cooperative multi-agent TSP? And so what we want to be seeing is something like this. So we have two agents, or in this case, in the central depot. And we're allowing each agent, one by one, to look at the world and understand it to make a decision. So what does understanding the world mean? So in this case, we're going to look at the blue agent first. And the blue agent looks at all, green agent looks at all of the cities that are open, right? Then it can look at all the other agents, so the second one, and it looks at whether or not it has decided a city, which is not the case. And based on this, it's going to make a decision. It's going to say, I want to go to this one. Now that this is done, the blue agent takes the role. So he's going to look at all the other cities that haven't been claimed. He's going to look at all the other agents and their decision so far. And he's going to make a decision as well. We start moving. and then let's move to this one. And we start moving, and then as soon as one of them reaches their first location, then the whole thing happens again, right? So this one is going to be able to look at all the cities that are still open, all the other agents and what they're going for, and then make a decision on where to go next, right? And then this whole thing happens. So in essence, that's very easy. Like it's obvious that that's what you want agents to be able to do, right? But to make this happen, we had to create a pretty interesting neural structure. We're allowing agents to start reasoning about what does the city, like open cityscape look like, right? Like, and then what are the other agents' states look like? And then start asking the question, where are other agents likely to be going next? Because at this point, you're starting to ask the question, you know, what are the saturated places that agents are already kind of en route to figure out, and where do I fit in? And that's really because of this that we're able to get this level of cooperation in the system, right? We also have a nice system at the end where the final policy scales naturally with the number of input cities. And that means that we have one model and you can change the number of agents, you can change the number of cities, you do not need to retrain, which is a very promising advantage. And again, like it's a lot of like neural network design in this case. We have two ways of using it. We have a greedy one where we just use the policy, take the highest one every time step, and we get pretty good performance, but about 400 times faster than state-of-the-art approaches. And we're okay using a bit more time. Then we have a sampling policy where we can sample multiple ones using the policy, kind of like this local search in conventional optimization and meta heuristic. And in this case, we get much better performance, but still a bit slower, right? What we're starting to see is that in small problem, we are beaten by those meta heuristic. Our tools from Google is our biggest competitor. And if you can use it, you should. But as soon as you go into difficult problems, we are able to beat it by quite a margin. We can beat it in like, so about 400 times faster in difficult problems, and we can very strongly beat it if we do the sampling strategy. And what is interesting is, why do we beat it? Our tools has this thing where if the problem becomes too large, it's going to decide to not deploy some of the agents. To reduce the search space, you're going to say, oh, I'm going to only use 7 of the 10 agents I have available. We're able to deploy all agents. It's a purely reactive, purely decentralized system. And as a result, even though our path may be slightly suboptimal, the overall gain is massive. And that's very appealing. We've done something like this for another problem extended from MTSP, where we just have like multiple agents that need to visit cities together. So essentially, they need to converge on tasks that might require multiple to do it. So think payload carrying or construction or something like this. And in this case, what we want to be able to do is have agents, you know, distribute and visit like single cities, but then rejoin at other cities. So essentially learn to form and disband dynamic coalitions, right? And so that was difficult to train. And in this case, one of the big contribution was how we allowed the training to happen through this leader-follower mechanism, where we're allowing agents not to all make decisions during training. We try to give structure during the training, but at the end, we still get a purely decentralized policy that scales very nicely and gets us, again, like a both better performance, but also a better trade-off of computation time and performance. We've done this for multi-agent path planning. We're getting back to it all the time, I know. So we focused on going away from this idea of a local field of view and allowing agents to really observe the entire system. So in this case, we have a lot of experience with graphs and graph transformers. So the idea is go from a specific world, create a graph over it, which is pretty easy to do. We just skeletonize the world and then we do it. But any graph that you want to do is perfectly fine, right? And then create clever features in those nodes of the graph that represents detour and like basically usefulness of those nodes in general. We also have the ability to start representing the rest of the agents. In this case, we're doing a heat map of other agents' position and their likely position in the next few time steps. We can't go full long-term in the future because a lot of it is going to be useless. But short-term, we have pretty good ways of predicting the movement, and so we can have this additional input. And when we put them together, we're essentially just adding an additional embedding to the original primal system, and we allow them to create this general context of the world, telling you this is the general like map of the obstacles in the system that will help you with routing, and this is the general behavior of the other agents that will help you with collision avoidance. And with this, we're getting very good performance. What is interesting is we're able to actually match and sometimes surpass the one I just showed you before with communication. So the idea here is that we do not let agents communicate. And yet, by just allowing them to have a larger and useful way of using this information, like visibility over the system, we're getting to the point that communication learning gives us. So those are essentially two different prongs at getting to the same high level of cooperation. And what I think is very interesting is, of course, it allows us to then start fusing them together, which is going to be our next step. Right? This is what it looks like in practice. Oh, good. Oh, say again? Sorry. Yes. Oh, EL is episode length. So the shorter is better, right? It's to give you an idea. And then AR is the reach rate. It's how many agents actually get to the goal. Because if you do only success rate, very often with learning and like decentralized approaches, you get most of them there, but not all of them. That counts as 0. And I think it's a very bad metric when you have decentralized. So I think showing you that whenever I tell you like maybe 0%, I'm still getting 25% of them on goal. I think it's interesting, at least for application, right? Yes. Exactly, yes. So in this case, it's trying to learn like bottlenecks and essentially like traffic situation, right? You know, where are many of the agents? Where will many of the agents be? And you're starting to like reason about those traffic conditions. Yes?
The OCR are
yes.
never bolted. And some of like the episodes like
oh, yes, yes. Yes, exactly. So the ODRN star is never bolded because it's the high ceiling of it. It's essentially because we've done it with like a bounded suboptimalities. It's not purely optimal, but it is like near optimal. And so it's not really a competitor. It's just to show you like how close we are in some scenarios to an actual optimal solver. Yes. What is interesting is to show again like the idea of like this routing. So if you look at primal and even a few other like communication-free methods in scenarios that are very tricky like this, so those 4 agents will exchange with those 4. You'll see that in some scenarios, some agents will never find a path to goal essentially, and we are able to do it like very reliably. So this is showing you both the level of cooperation that you get from having to go through this bottleneck, but also the ability to find a path to go, which is coming from this global graph, right? Because even in methods like DHC that give you a underlying A-star map that agents should be able to leverage to get to their goal, it's not always clear and easy to use this thing, whereas the graph seems to be a better representation to actually get efficient routing to the goal. So I can play this again, right? But if you look at it, right, you see that those are all communication-enabled methods, right? But even in some that have global guidance, it takes a lot longer, and sometimes they just cannot find a way to go for all agents. Even though this seems like an easy path, but you know, it's difficult to have this reactive, somewhat greedy approach that gets you to goal if you don't have the full knowledge. We're also able to run it on robots. This is a very simple demo, right? Just 3 robots handling an interesting bottleneck, and this is running on hardware. We're running on like a receding horizon planner for this one also. So that's pretty nice. And then the last part of the talk. So it's just the last 10 minutes, right? So going towards heterogeneous robots and heterogeneous teams. So of course, a lot of what I've shown you is what is interesting maybe in applications today, a lot of homogeneous robots in controlled environments. So scalability matters, but all robots are the same. And there's a lot of assumptions you can make in terms of like speeding up the training and also learning something that's a bit simpler. But a lot of the future, at least the future that we might want to see, involves many robots of many kinds, either you know, operating in the same scenario or even operating together. You can think of, you know, for search scenarios, like you'd like to deploy as many robots as fast as possible to speed up search after like a disaster, and you don't care about the robots you have. You just want them to be able to work together, leverage synergies. You don't want to, you know, have to specifically say, oh no, I can't use this one because I don't know how to make it work with the other, right? There has been work recently on like easy heterogeneous systems. You see perseverance and ingenuity. This is just 2 robots working together, more like a marsupial multi-robot system. The one we've been caring about a lot is this search idea. So coverage or multi-agent search and being able to leverage the motion and sensing abilities of different robots to search better. You can see in this case, for example, like a high-flying drone will be able to see more of the ground, but maybe at a lower resolution. And maybe it would be a good way of like connecting with the others for communication, right? But then a lower to the ground point of view can help you search under the trees, whereas flying robots are, you know, faster and more mobile, but they might not be able to always have the same vantage point, right? So like reasoning about motion constraints, motion abilities, and then same thing for sensing, right? So the way we've actually looked at it is through the lens of ergodic coverage. So the idea here is we assume that we have a prior over the distribution of information in the domain, right? So it can be presence of target, or it can be like, a temperature of some underlying field that you would like to sample or reconstruct, right? And if you have this prior, we're starting to do trajectory planning. We would like agents to create long-term trajectories that are ergodic with respect to this underlying prior, right? Which means that they will spend time in areas in proportion to the expected information in that area. So what it means is that if I have an agent and yellow means a lot of information, I want the agents to be a lot more in the yellow than in the blue. But I would like to also naturally balance exploration exploitation. So since blue is not zero information, I still would like to have some visit there, just much less than in the yellow region, right? And so the way we do it is we can't compare distributions very easily, but we can compare their representation in another field a lot easier. So what we do in this case is, and this is work by Igor Mesic and Matthews, we represent the distribution, the prior, and the agent statistics, the path distribution, as Fourier coefficients. And we look at the mapping between, like the resemblance between those Fourier coefficients. And you see that the metric, like this distance between the distribution, is a sum of the distance between their coefficients, right? So we'd like those coefficients to match, and then we say, hey, you seem to be having a distribution of presence in the team that resembles the distribution of information in the space, right? Oh, yes. It's the coefficients of the density. Yes, the Fourier representation of the density. Yes. Did I say it wrong? I'm sorry. No, yeah. No, yeah. So essentially the idea here is that we're saying, let's do distribution matching in the spectral domain, because it's difficult to do it directly like this. We can do like Earth moving distance, you can do KR, but this is a lot easier to define. The big advantage is by going through the spectral domain, you can start also making sense of those coefficients. So for example, if you're looking at coefficients of low frequencies of this distribution, right? Those correspond to like slower movements of like changes at the overall scale of the system, right? And they might be better suited for an agent like this, right? A more omnidirectional agent with high range but low fidelity sensor, right? And on the opposite, if you're looking at more of the high frequency coefficient, they represent more like peaks of information, more details. And those ones might be better to be connected by curve constraint agents with more focus, so lower range, but high fidelity sensor. And so if you make this assumption, we can start distributing the agents by telling them, don't be ergodic on the overall distribution, be ergodic on essentially an intermediate distribution that we reconstruct only from the coefficient we think are good for you. And again, like here, this is just the first step. We're just saying, hey, we think we have some intuition about the distribution, so let's use it to see if it makes sense. And so this is helping a lot with the distribution of the agent over this map. And we're starting to get the idea of, this 1 + 1 is larger than 2. So the results are showing that in this case, if we just distribute the two agents, we get better than if either of them was deployed alone. But if we distribute them with this distribution of the spectral bands, then we get much faster time to find target and much better reconstruction of the underlying field. Now, this is us saying we are good at distributing the agents. What about agents being good at doing it themselves? And so our most recent work was on allowing agents to learn their own capabilities. So answering the question, what am I good at, right? We're not yet at the point of answering the question, what am I better at? Which means I understand myself in the context of my team. That's, a next step. But for now, we're asking, if I assume that I know nothing, like I might be good at all bands, right? How do I learn, to get better at understanding myself? So we have different ways of representing like the threshold directly through each, like my interest, my attention over each of the bands, right? Or as a parametric representation, like in this case, a Gaussian over the domain of frequencies, right? But in all of those, we're learning something like this by the end. We're learning, like one agent is very good at low frequencies, the other one is very good at high, and we're looking at it very cleanly. So it's very similar to the intuition we just had and used in the previous one, but this is learned. So it's confirming that the agents would learn the same thing. If we allow them to really learn attention over each of the bands, we're starting to get a slightly better results, but it's a lot more messy. I feel like it's not really getting just the perfect, like, structured result. And if we're learning with a parameterized curve, then we got, again, like getting those nice distribution. And this one is a lot easier to train because you're only learning fewer parameters, right? Again? Oh, Xi. Yeah. Xi is the Fourier coefficient. It's I think this one. Oh yeah, it's the Fourier coefficient of the underlying distribution of information. So basically, it's always a comparison between the two coefficients. One of them is the coefficient of the distribution, what we call the time average statistic of the agent. So it's where the agent has been and how much time or how much proportion of the time was spent in this area. And the other one is the Fourier coefficient of the underlying prior. And we'd like those two to match, right? Yes. Yeah. I think, yeah, this one depends on gamma, so it depends on the path, and then the other one is the info, the prior info, right? So this is all assuming, by the way, that we have accurate prior over the distribution of information. It's just about, if I know my setup, how do I distribute them really well? And what you see here is finally this 1 + 1 is larger than 2. So you see that if I distribute two agents, I'm getting, lower ergodicity. Lower is better, right? So it means that, with more agents, I'm getting better than if I only had one of them, of course. But if you start being good at distributing them according to their individual abilities, their advantages, then you're getting even better than just having scale work in your favor. So this is really showing you that if you do spend a bit of time and effort in figuring out where agents are good, or if they can do it even for themselves, right, you are getting those super linear gains that we're hoping in collaboration scenarios, right? And so with this is what we've done so far. So I've shown you a lot of what we did earlier in the CTD paradigm, right? So being able to do parameter sharing, so learn a common policy that we can learn faster by leveraging experience from multiple agents, and then we can copy with pretty much arbitrary scalability, right? Then we went into cooperation, where there, like, scalability is a little bit harder because we add interaction between the agents, right? So convention learning was an easy way of extending, right? So this one doesn't really suffer from the scalability issue. When you go into communication learning, of course, scalability is a big challenge, like dealing with many messages, conflicting messages, etc. Context-based learning is also another way, without having explicit interactions, to bake interactions into a context that agents can use, right? And then for heterogeneous teams, so we haven't really focused specifically on cooperation yet, but we have at least focused on, the collaboration problem. Like, how do I figure out what I'm good at and how do I fit into, right? Ongoing work, so we've started working a bit more on aspects of predictive, right, or modeling-based cooperation between agents. So we have some work on intent sharing, so allowing agents to use their own policy to predict where they will be in the short term and propagate this in the team. It's essentially allowing them to claim areas, especially for search, right, that others maybe shouldn't go to, right? And even when those claims are not always correct, agents are able to learn through attention that some of it is correct, some of it you might change, and they're kind of figuring out each other and how they claim areas. We've done some work, and we're starting to do some work on explicit teammate modeling. So there's been some work before where you do learn somebody else's policy, and I think that's a bit too limiting, like, for scalability. But maybe through diffusion models or other methods, there's ways of at least understanding what are other agents doing as a whole, maybe not individually. And then very interesting, I feel like the same way skill learning for single agent is allowing you to do temporal abstraction, so abstract a sequence of action instead of just doing one by one. I think strategy learning could allow us to abstract cooperation in a team and allow to do, like, essentially kind of like the football of, I want to do this strategy, and then next one will do this one, and start abstracting, like, cooperation as, like, sequences of strategies that we're enacting. So giving us temporal and cooperation abstraction. And with this, I wanted to thank everybody that was involved. Thank you very much for your time and attention, and I'm open for questions.
Thank you for the talk. So now we'll be taking questions from both the online and offline audience. So if you have a question, please raise your hand in the auditorium and I'll pass the mic. Or online audience.
I have a question there.
So could you introduce a group of new agents to learn existing coordination strategies by observing the others that already have an existing coordination structure?
That's a really good question. Yeah, so it's going into the realm of like teacher-student models, right? Essentially, you can do this. I think there's a lot of work on this. I've never worked on it personally. There's a lot of work on this, and you can also do it through just imitation learning, right? But I think the interesting part is not just observe the other, but kind of interact with them, right? And that's more like teacher-student models. So that's a branch of multi-agent like learning, but I don't have anything in it.
So like
right?
if I go to the UK, I know to drive on the other side of the road, that sort of thing.
Yes,
Basically,
exactly.
To keep
Yes.
it as a simple.
Yeah. No, it's feasible. Yeah. And it's also a promising way of doing it, especially when we start like being better at learning on hardware. For now, the big limitation is since we do a lot of training and simulation, then you don't need to solve this problem too much. Go for it, sorry.
So it looks like in a lot of the models, a consistent understanding of the world for each agent is needed. But when an agent is actually observing the world with a camera or LiDAR, it might actually see different information compared to its neighbors. Are there any good ways to deal with that slight discrepancy?
Yes. Okay, that's a very good question. So that's something I actually didn't mention because it seemed like a detail, but I'm happy with touching on it. So a lot of our assumption, right, is like you can see around you as if you had like a bird's eye view, like it's just magically, right? So this makes actual implementation a little bit more difficult. So you can train with it and it usually kind of works. The two answers that you want is you can definitely use comms learning as a way to augment the field of view of somebody else and kind of like, complete those areas that are in shadows through obstacle for somebody else. The other thing is the work I showed you with this like communication learning for MapF, we actually restricted the field of view to be 3 by 3. So our assumption there was like, hey, if we have a LiDAR, at best, I can see only one cell around me. Because worst case, I have like 8 agents around and that's blocking my view past it. So we were doing this with very small field of view and communication learning. So it's exactly doing this, like, augmenting the field of view and really focusing on cooperation and like in the communication as the way to drive agents to their goal, as opposed to just understanding their local field of view and just relying on it, right? So it is feasible. It is more of a challenge, but yeah, it's essentially the answer is design your training a little bit to it and you kind of get it for free.
A great talk, great talk. So I have two questions. One is, can you think of like collaboration, but with separate teams? They are still in the same environment, but the teams need to have some diversity in their approach. So that's one question. And then the second one is that now, as you go from collaboration and cooperation, how does it change the structure of the problem when you introduce some adversarial agents? Maybe?
Yes.
And because if you use mean field games, how do you change, how do you extend mean field games for this diversity? And then
Yeah. No, this is a good question. Okay, so the first one would fall a little bit under this kind of like middle section that I kind of ignored a little bit, right? The kind of hierarchical control, right? So you have essentially some sort of overhead or like interactions between different groups of tightly coordinated agents, right? So I haven't done a lot of work there. I'm more of a decentralized person, right? But they're all work that are trying to extend some of what I discussed, especially the value decomposition one, like QMix and the likes. Two scenarios where you have multiple teams working together. So they don't have to be heterogeneous team, but with QMix they are, because you're learning single agent policies that are completely independent and usually are different because they interlock well together. So they're not heterogeneous agents, but they are heterogeneous policies. So it's just somewhat similar, right? Essentially, it's allowing agents to take on roles, even though their capabilities might be generic, right? So there is a lot of work on this. That's something we haven't done too much because for now, in terms of application, that's less of an interest for like robotics, but for AI, there's a lot of work on it. But the second one, it was about adversarial, right? So there's also some work that I know. So I know like Amanda Prorok, for example, she started working a bit on like adversarial comms and adversarial like, behaviors. So I don't know if kind of like the mean field approach is the right way at this point, or like the context learning, to call it this way, right? Is the right way to do it. I feel like it would start going through a different route. Like it would go closer to what I discussed at the end. This kind of like, modeling of your neighbors. Because at this point, you don't really want to know what the team is doing. You'd like to start going back to being a bit more microscopic and being like, hey, can I trust this guy or this guy? And it doesn't have to be like so specific, but it can be just some sort of attention on the others or something. So that's something we haven't done too much. Again, a lot of interest in like pure AI, a little bit less so in robotics for now. But yeah, but this is all like very open directions, by the way. So this is very good.
So I think it was in Scrimp.
Yeah.
Could you kind of learn what areas to avoid, and particularly if there's noise? So for example, you might, if you have a lot of agents and you have a narrow bottleneck, it might make sense to take the longer path that's open. And that could be some generic thing that you could learn that's conditioned on the number of agents. And I guess an extension of that, would you see any benefits to potentially GANing that?
Oh, GANing? Yeah. Like, you mean like generic? Yeah. Okay, so Scrimp was the one with communication, but no global view, right? That's the one you mean. Okay, yes. So they are doing a little bit of this, but admittedly not as well as Alpha, the one with like global observation, right? Because they are communicating with everybody. We also tried like local comms, but it wasn't really improving that much. Scalability of transformers is so good. So they are communicating with everybody, and they can see where agents are more present. Like they can get an idea, kind of like Google Maps, you use your GPS, and then everybody knows where people are using the GPS, which means it's congested, right? So they are getting this through comms, and they're using it a little bit to do rerouting. But I think if you want to really go for like this global level rerouting, then going with something like Alpha with like this global representation of the world is better. I think that's the solution. Now, can we GAN it? Yes. I mean, I think that's the idea. So that's part of what we want to be doing, like this this second one that I mentioned here. That's what we're starting to do. So either GANs or generative models, like a diffusion model, is to kind of predict the large-scale traffic scenario in the world. And I think that's going to be like a very, I think, very potent addition to the observability of the agent. Yeah.
Yeah, so I have a question
Yeah.
that has slightly different flavor. You showed in the previous slide for the centralized multi-robot systems, we already have a lot of applications in the industry like Amazon Robotics. But for decentralized, so the two examples, Ant, which is a biological system, and also the Kilobot, which is an academic endeavor, which is super cool. So what is really preventing a decentralized multi-robot system from being applied in the industry? And if there are already applications, where are they?
Yes. Okay, that's a very good question. So I'll just go to the slides so this way we're all looking at the same thing. But yes, I think the broad answer is that in industry right now, we're not having like that big of a team, right? Essentially, in this very controlled environment. And so we want the performance guarantees. We want the oversight, like the fact that I can monitor my whole team. So centralization is good, right? It's not really a caveat. And I think the applications are a lot more in like autonomy. So of course, like anything, defense, like civilian defense and everything is interesting, right? But in any application where you will not, you cannot assume this centralized monitoring, and you actually want agents to be more independent, because this way you can't have a communication severed and now you're in trouble, or if an agent crashes or is in a dangerous scenario, the other ones will react accordingly, right? So I think like more defense scenarios are the ones that drive decentralized systems, and then just general interest. My impression is that we're still at the early stages of multi-agent autonomy, and at this stage we're a little bit worried about fully letting them go wild. And having this level of at least monitoring, so centralized monitoring, is okay. Like it's not limiting performance, and it's reassuring people. So I think this is really what's driving it for now. But as soon as we get to like larger teams or to a level of single agent autonomy that we really trust, then we're going to see those decentralized systems come out a lot more, because it's the future. I mean, we don't expect oversight over, centralization of humans. So we won't do it for robots long term.
Thank you.
Yeah.
Let's thank our speaker one more time. So please tune in next Friday, February 23rd at 10:30 Eastern Standard Time for our next Grasp on Robotics talk featuring Pietro Valdastri from the University of Leeds. And to rewatch this talk or any of our past Grasp on Robotics talks, please visit our Grasp YouTube channel and website. And for more information on upcoming events, be sure to follow us on social media. Thank you again, and have a wonderful day.